Good morning, everyone. Good morning. Hope all is well. Hope everyone's doing all right. As always, want to give everybody a few seconds to connect, then we'll get rolling. Okay, it looks like everybody's in. Once again, good morning, everyone. Hope everybody's doing great. Hope you had a great weekend and ready to get this week started. So last class we ended with I believe we're in the middle of 5-2, and of course, if I'm a little off, then let me know. But I believe we left off in the middle of 5-2 doing the addition rule, and we're now at the general addition rule. Because let me see, making sure single dot toss. That's the integrating 3. I believe that was it. I believe we are right here. Middle 5-2 alcohol. All right, sounds good. Thank you, thank you. So we're looking right here at the general addition rule. You want to know the probability of E or F occurring. We would take the probability of E plus the probability of F, and then we're going to subtract what E and F have in common. And so that means that E and F are not mutually exclusive. Remember, if they're mutually exclusive, they have nothing in common. And then that's why we wouldn't have to worry about this piece over here. And so we'll see why this is the case in a second. Yep. We have to consider what they have in common. Yep, and you'll see why that's important in a second. When we look at this next problem. Pretty good. Can we scroll up? Okay. So we have a single dice toss. Find the probability of rolling an even number or a number less than 5. All right. So our sample space, we talked about a single die has 6 options, the numbers 1 through 6. So we see that in the red. You always, whenever dealing with probability, is always easiest to go ahead and establish your sample space first. So 1 through 6, we have 6 options total. So the number of my sample space is 6. The first event is rolling an even number. And from 1 through 6, we have 2, 4, 6. And so that's 3 options. So the probability would be 3 over 6. All right. So the next event was less than 5. So in the sample spaces of 1 through 6, the values that are less than 5, we have 1, 2, 3, 4. So that would be 4 numbers that fit that description. And so we place the 4/6. So before we look at this orange, is everybody okay with the purple and the blue? Those are the events that they gave us, wrote in an even number or a number less than 5. All right. So now looking at the orange, we're talking about being even and less than 5. So notice I wrote right here in red that the numbers or the events, excuse me, are not disjoint. The events are not mutually exclusive. Remember, disjoint and mutually exclusive are the same thing. So that means they have something in common. If you notice, we have 2 and 4 that are even numbers and 2 and 4 that are less than 5. Now, it's important that we consider what they have in common, because what you don't want to do is count 2 and 4 twice. You don't want to count what they have in common twice. If I were to add 3/6 and 4/6, that'll give me 7/6, which would give me a number greater than 1. Remember, our proportion, not proportion, our probability cannot be greater than 1. So you should know that something is wrong there. But the reason why is because we're counting 2 and 4 in this number here, and we're counting 2 and 4 in this number here. So we don't want to count 2 and 4 twice. So that's why we consider what they have in common, which is 2 and 4. And the number of items that they have in common is 2, 2 and 4. And then that's why it's 2/6. All right. So make sure we are clear with our 3 pieces before we plug them into the formula. All right, so plug them into the formula. Probability of E plus the probability of L minus the probability E and L. So it's 3/6 plus 4/6 minus 2/6. So they give me 5/6. All right, questions. All right, anybody still copying before I scroll up to the next one? All right, next one. A single card is drawn from a standard 52 card deck. Compute the probability of the events of drawing a king or drawing a diamond. All right. Sorry about that. So when we're looking at our events, just like before, you want to ask yourself, are the events mutually exclusive? In other words, are the events disjoint? So just trying to drive home the point that disjoint and mutually exclusive are the same. So no, they do have a card in common. When you talk about kings, you talk about diamonds, there is such thing as a king of diamonds. So there is a card that is a king and a diamond. So we do have to consider that because in the number of kings is the king of diamonds. And then in the number of diamonds is the king of diamonds. So you don't want to count the king of diamonds twice. So there are our three pieces. We have the kings, the diamonds, and then the king of diamonds. So in all cases, our sample space is 52 because there are 52 cards in the deck. There are 4 kings. So that probability to get a king will be 4 out of 52. There are 13 diamonds. Remember, each suit has 13 cards in it. So that's 13 over 52. And then the king of diamonds, there's only one king of diamonds. So that's 1 over 52. Any questions so far? Any questions?
Yeah, I have a question.
Mm-hmm.
I had a dog that was barking, so I think I missed it. Under King and Diamond, when it says N, K, and D equals 1, what's that from?
Oh, there's only one king of diamonds.
Oh, okay.
Yep. So, and just running through it just to make sure everybody's with us. So it's a good question. So these numbers right here, everybody, well, all of them are 52 because there are 52 cards in the deck. So we're not changing decks for each event. And then here, there are 4 kings in the deck. There are 13 diamonds in the deck. And then there's one card that's a king and a diamond. That's the king of diamonds. And then you place each one of those over 52. All right, scrolling up. Once you have your 3 pieces, you place it in the formula. 4 over 52 plus 13 over 52 minus 1 over 52 gives us 16 over 52. And then notice we can reduce it. They both have 4 in common, so we cancel out the 4s and that'll leave us 4 over 13. All right, any questions? Any questions? All right, next we're getting into the complement of an event. So all the outcomes in the sample space that are not the event or not in the event that you're describing. All right, are we done with that last problem? Very good. Okay. So the complement of event E will be notated by E with the superscript C. And we have the complement rule. These are just variations of the same relationship. Just saying that if you know the probability of one, then you can find the other. Because if you have the probability of your event, if you subtract it from one, that'll be the probability of the complement of your event. If you know the probability of the complement, subtract it from one, that would be the probability of your event. Or in other words, if you were to add both of your probabilities together, the probability of your event and the probability of your complement, then they will add together and give you one. All right. I keep scrolling. Okay. So just wrote ACC for that, according to the National Gambling Impact Study Commission, 52% of Americans have played state lotteries. What is the probability that a randomly selected American has not played a state lottery? All right. So to give us the probability that someone has played, and if you want to find the probability, that someone has not played, you will subtract that from one. So 52% is 0.52, 1 minus 0.52, 0.48, or in other words, 48%. All right. Any questions? Any questions? All right, can I scroll up? Very good. Don't worry about this. Somebody asked me something. So very good. That last one. Okay. So 5.3, independence and the multiplication rule. So two events are independent if the occurrence of one event does not affect the other. Two events are dependent if the occurrence of one event does affect the other. So in other words, the other one depends, one event depends on the other. So it means they're dependent. All right. So next exercise is just going to emphasize the idea of two events being independent or dependent. So suppose you flip a coin and roll a die. Are the events obtain a head and roll a 5 independent? So in other words, when you flip this coin, when you roll the die, does one depend on the other? Does one affect the occurrence of the other? So it says, are they independent? The answer is yes, they are independent. One has nothing to do with the other. So if you flip that coin, it does not affect the probability that you will land a 5. All right. Any problem with that? Next one, are the events earned a bachelor's degree and earned more than $100,000 per year independent? All right. They are not independent. Earning a bachelor's degree increases your chance of earning $100,000 or more. So it doesn't guarantee that you will make $100,000 or more, but once again, we're talking about increasing the probability. It increases your chances of making $100,000 or more. All right. Questions? Any questions? Can we scroll up?
right, so multiplication rule for independent events. So notice it says if your events are independent, so that will be something that you will have to establish first. Make sure that the events have nothing to do with each other. You know, we are going to deal with dependent events. I believe that's in 5.4. So, but we will look at what happens when we have events that affect the other one. But right now we're talking about events that have nothing to do with each other. So we want to find the probability of and. Remember, last section we were looking at the probability of or, probability of an E or F occurring. This time we're looking at the probability of E and F occurring. So this time you have to multiply. Once again, for or, you add your probabilities. For and, you would multiply your probabilities. Okay. And keep in mind, you know, I know it may be a lot of formulas and stuff like that, but make sure you're taking good notes so that you can be, you will be able to reference them. Remember, whenever you're doing your tests, if you have access to them, it's not like I'm taking your notes away, or your ability to use your notes. So make sure you're taking good notes. You know, you're gonna see you have the videos. So even if you hadn't written down everything right now, you can always go back and review and the videos, pause them, write down whatever you need to write down, all the good stuff like that. So make sure that you're writing these formulas down. Make sure you're notating the difference, and what you're seeing and all the good stuff like that. So you write down the formula if I scroll all the way up. All right. So in the game roulette, the wheel has slots numbered 0, 00, and 1 through 36. A metal ball rolls around a wheel until it falls into one of the numbered slots. What is the probability that the ball will land in the slot number 17 2 times in a row? Give you a chance to write that down. All right. So first thing we need to do, establish, are these events independent? And they are, because the occurrence of rolling a 17 does not affect the occurrence of rolling 17 again. All you're doing is rolling a 17 and they take your ball out and roll it again. So just talking about rolling 17 twice. It's not like they roll a 17, then they let you roll the first time, then whatever you hit, they block out what you hit, and then you can't hit that again. So that's not, they don't take anything, they don't alter the wheel. So the ability to roll 17 2 times in a row is not does not change. All right. So after you establish that they are independent events, now you can go about finding the probability of each event. In this case, both of them are the same because we're talking about rolling a 17 twice. So we have 38 numbers. So if you go back, that's why I have green, circled in green. You have 0, 00, and then 1 through 36. So that's 38 numbers or 38 options. The number 17 is only one number 17, so it's 1. And that probability is 1 over 38.
Everybody good? Anybody still copying the red? So, all right, hold on. Somebody said something. Okay, let me cut back down to the red. All right. All right. Right down with the red. So now we just follow the formula. Both of our events is rolling to 17, so we have 1/38. We already established that's the probability of rolling to 17, and we established that that probability does not change. So it's 1/38, and you multiply them, that'll be 1/1444. And just pay attention to how Math Lab wants you to answer this. They either want the fraction, or they ask for the decimal, and it's just 1 divided by 1,444. 1,444. And once again, pay attention to how many decimal places they want. Probably don't want that many. I was just giving you, enough. All right, we'll go to the next one. Very good. Okay. So we have the probability that a randomly selected 24-year-old male will survive the year. It's 0.9986 according to the National Vital Statistics Report. So A, what is the probability that three randomly selected 24-year-old males will survive the year? Then B, what's the probability that 20 randomly selected 24-year-old males will survive the year? All right, scroll up. So in the red, we see, we want to once again make sure we have independent events.
So yes, they are independent. One 24-year-old male surviving a year has nothing to do with another randomly selected 24-year-old male. So we're not talking about, two people that have beef and all the stuff like that. We're just talking about randomly selected, randomly selected. So those events are independent. And they gave us the probability that that 24-year-old will survive the year is 0.9986. So the probability that all three will survive, since they're independent, we just take that probability and multiply it to each other 3 times. And right here in that circle blue, I was just showing how you could put it in your calculator, that symbol. Some people have the cubic button or the cube button. Some people may have to use this hat, or sometimes it's called a caret. Some people may have this as an option in the calculator, where you can put a number right here and a number up here for your exponent. But either way, whatever way you have, you need to multiply 0.9986 times itself 3 times. And the reason why I'm emphasizing that right now is because of the next problem. Just typing out 0.9986 3 times is not a big deal. But then when you have larger numbers, you want to be able to raise it to an exponent. So 0.9986 3 times will be 0.9958. Any problems with A before we go to B? All right. So the next one was what's the probability of that all 20 survive? And so that's 0.9986 to the 20th power. So here you don't want to have to write out 0.9986 20 times, and trust yourself to do it accurately, because we're all human. It's easy for us to make mistakes. So it's best to do 0.9986 to the 20th power. And so that's all about making sure you have a device that can help you out with that. All right. Any problem with that before we go to the next one? All right. Everybody done with B? Okay. So here, compute the probability that at least one male out of 1,000 24-year-olds will die during the course of the year if the probability that a randomly selected 24-year-old male survives the year is 0.9986. Give you a chance to write that up.
All right. So here we're going to use the complement rule. So we're trying to find the probability that at least one male out of 1,000 would die. So remember, we have the probability that all will survive. Now we're trying to find a probability that at least one out of the 1,000 will die. So the way we do that, we're talking about at least one dies. We're going to take the probability that none of them will die and subtract it from one. So, you know, if you say at least one die, that means you're talking about one die. The least is one die. So one die, maybe two die, three die, four die, all the way up to all of them dying are part of that probability. So we take the probability that none die and then subtract that from one. And that will be our answer. So that's 1 minus 0.9986 to the 1,000th power. Once again, emphasizing the idea that you're going to have to use your calculator. You don't want to try to multiply 0.9986 1,000 times. So that gives us 0.2464, and that's 0.7536. All right. Questions in these questions? All right. So that's 5-3. So next class, we'll get into 5-4, and that's going to deal with the probabilities that are, or events that are dependent. So here we have conditional probability. So we'll look into that next class. So before we close, do we have any questions? Everybody good? Everybody straight? All right. So if you guys are good, I'm good. Next class, we'll get into 5-4 and try to close out chapter 5 and go from there. All right. So you guys have a good one. All right. Somebody said they have a question, and I'm all ears. I don't know if you want to chat it or
Mr.
unmute.
Tucker,
Yes.
I think I sent you an email about me and my sister going away for a while
Mhm.
from March 13th to the 22nd.
Mhm.
Do you, and then we want to get ahead on our work. So is there any way you can pre-record the lessons maybe for?
I can give you the lectures from last semester. I already talked
Okay.
about it. Yeah. So yeah, email me again. Just something to say, yeah. Just reminding you to shoot me those video lectures, something like that, and I'll shoot them to you.
Okay.
Yeah.
Thank you.
Yep. I need you to email me because I'm gonna forget. So I need you to shoot me that reminder. All right.
Okay.
All right. Mhm. Take care.
You too.